Hello everyone. So today we'll be going over building a decision tree from scratch, all of the theory, and a basic implementation of a decision tree. Now we won't be implementing the entire decision tree class like it's written as scikit-learn. It would be like reinventing the wheel. It's already there. This video is more for your understanding, more to clear your doubts regarding how decision trees are actually built. So let's jump in straight. So let's begin with theory. Now, we'll be using Gini impurity to make a split-centered decision tree. Actually, we'll be using information gain, but to calculate whether how pure a particular split is, we'll be using Gini impurity. Gini impurity is nothing but 1 minus Gini, and the Gini formula is the summation of all the probabilities of the class ranging from 0, 1, 2, 3. So if you have two classes, this will be like, let me just quickly, yeah. So sorry, this will be like 1 minus probability of class 1 square plus minus probability of class 2 square. Hopefully this clears it of how to calculate it. And now how do we actually determine the split? How do we make sure that on which one should we split it? So for this we use information gain. Here you can read through it, what information gain is. I'll be linking this GitHub gist in the description of this video below so you can check it out. So information gain is a measure of how much information a feature provides about the target variable in a decision tree. The idea behind using information gain is to split the data into distinct groups, and the one which gives the information gain the most, we use it to make the split. The information gain of the sample given a feature A is the information. So in this case, the information gain we are using Gini. So Gini of the entire sample minus Gini of the subset. So this is an averaged Gini of the subset. We'll go much more detail into the calculation of all of this. So if in case you're a bit thinking that this does not make sense, stick around and it will start making sense to you. So as I said, where S is the set of all samples, A is a feature, G of S is the Gini index of the target variable for the set of all samples, and G of S given A is the weighted average of the entropies or sorry, weighted average of the, it's not the entropy, it's the Gini uh, impurity of the target variable uh, for all samples given in the feature A. When the information gain is high, it means the feature A is able to separate the samples. When it's low, which means the information gain is close to zero, which means that it's more or less there's no point in making a split on that variable. We'll see this later on that when the information gain is zero, that essentially the probabilities in a binary classification are 50-50 in that particular split for the target. Now, this is basic theory. This should be more than enough to tackle any decision tree question coming along in a data science interview. Uh, and now that you have gone through the theory, let's just go over a dummy example. Now I'll be creating a dummy data. The dummy data will be like the target is whether someone will go out to play or not. And we will have four features. Each of these features are also binary to make calculations and understanding easier. The first feature is whether it is sunny or not outside. The second feature is whether do we have more than 10 players or not. The third feature is whether football is being played. And the fourth feature is whether I'll be playing in the morning or not. We could have gone for more features, but for right now, we are focusing only on four features because we want to understand. And the target is again whether we are going to play or not play. So let's just load our libraries. Here I already have the data constructed, dummy data. As you can see, we have around 12 samples with the target variable whether we'll play or not. Now, let's say we want to calculate the information gain for each of these variables. So first we'll build our helper function. So we'll first build this one, which is Gini impurity. This one, yeah. So the Gini impurity, as we know, is just 1 minus the sum of probability square. So it will be uh, probs will be np dot bin count. If you don't know what np dot bin count does, let's say you have one np dot bin count. This is just 1 1 0 0, say 0 0 1 1. You see, it just calculates the count of the individual classes. And to get the probability, it's just divided by the length of x. So uh, if you divide it by 4, you would see it gives 0.5. The value gets broadcasted. That's the best part about NumPy. And we get probability squares. So here will be, uh, if you just take the squares of it like this, you get 0.5, and just sum it up. Uh, sorry, yeah, sum this up. You'll get 0.5, and uh, you get the Gini impurity is 1 minus. So this is essentially the most impure that you can get. As you can see, the Gini, the maximum range of this can go from uh, 0 to 0.5. This is something which I missed here. Gini goes from 0 to 0.5, where 0 is the most pure and 0.5 is the most impure. In this case, you'll see that 0.5 is the most impure that you can get. Okay, all right. So we have our Gini impurity calculator, which we have. Uh, this helper functions, and then we have to calculate the information gain. Information gain is the Gini impurity of the whole sample, which is the parent minus the Gini impurity of all the subsets, the weighted average. Here I have again written a helper function to guide us through it, where the information gain, so information gain for which feature we are trying to calculate it, the data on which we are trying to calculate it, and what is the label. We have already defaulted label target because that's what the naming is. And then I'm just saving Gini impurities here. So for in this case, it will be for threshold in np.uniquedata.feature. I'm not doing anything. Let's just take an example of sunny or not. So here will be threshold will be sunny or not. Or not. And for unique, so we have only two unique values. So first it will be for 0, for sunny or not in 0. It will calculate Gini impurity and it will divide the data where the feature is 0 and for the target, and then weighted Gini impurity is nothing but the number of samples where that particular GI is 0. So for example, let's just do a quick calculations for here, a dirty calculation here. So for sunny or not, if you want to do this particular function, it will be uh, sunny or not 1. So the data will be, the Gini impurity will be, uh, let's just do, let's just calculate Gini impurity here using this helper function, and here x will be data, data dot sunny or not is equals to 1, and we have the target here because that's what we want to calculate it upon. It will be 0.46875, and this is we get for sunny or not 1, and if sunny or not will be 0, we'll be getting Gini impurity as 0. We got both the Gini impurities, but the information gain will not be, and the whole Gini impurity of the entire target is just Gini impurity data target. But the information gain, and since there is no, because there are 1, 2, 3, 4, 5, 6 ones and 6 zeros, essentially the G will be 0.5. This is not by chance, this was designed to be the case. Here it will not be 0.5 minus 0.46 0.875 minus 0.375, because we have to weigh each of these, this one. So the weight is nothing but uh, this dot shape 0 divided by data dot shape 0. So the weight, sorry, okay, so, we don't need this one. Yeah, so this is 0.66. I'll just enter, and this will be this is definitely 0.33, just making sure. So this will be the Gini impurity. The information gain will be roughly 0.67. Uh, this is what the helper function here should also produce. So this is what the information gain function really calculates. Uh, Feel free to check it out. But as you saw, this is the rough calculation which I saw. This is what it actually does. So here uh, for each of the features, I've calculated the information gain. As you see, we get roughly equal calculations. I've limited it to 3 decimal places. Obviously, uh, I can make it 4, and you'll see 0.625. And so information gain for more than 10 players, football player, and its morning is this much. Now, based on this, obviously the information gain is highest for the feature sunny or not. So, if that is the highest, we will be using that to split our decision tree. Now, using this, now once you split the decision tree at sunny or not, you have to split it again. And how will you decide which one to split? So, sunny or not, so the let me just open draw.io. And so right now the decision tree will just look like sunny or not, with left going 1 and right going 0. Now, how will you determine again what to split? So you will have to do a recursive uh, call. So I have done here again, not recursive call, but you have to do again, you have to do for all the features which are not sunny or not, to see in that particular split which one should be used. So again, if you see, I have taken the features more than 10 players, football played is morning, and then for all of them, and then for I in np.unique data sunny or not. So basically splitting it into where sunny or not is 0 or 1, and then again for the features, for all of the features, I'm calculating the information gain based on that particular subset of the data. When subset of the data sunny or not is 0, and subset of the data sunny or not is 1. So here, when I do this, I see that the split for sun when sunny or not is 0, we see that the information gain is highest for the feature is morning, and when sunny or not is 1, I see that the information gain is highest for the feature football played. So let's just visualize these two. So basically, when sunny or not is 0, it is saying that the information is highest for is morning. So for is morning, we see that when is morning is 0, the target is always 0. When is morning is 1, the target is 1 once and 0 once. And for data sunny or not 1, the highest information gain was for football played. For football played, we'll see it has 1, 2, 3, 4, 5, 6, 7, 8 samples. When it is 1, we see that the target is always 1. And when it is 0, we see the target is 1, 1, 2, 2 times out of 5. So let's assume that our decision tree ends here. So how will we calculate what is the probabilities in this leaf? Basically, if this is the terminal node, what is what is the probability in the leaves of this terminal node? So it's very simple. We just take the value. So for example, in this one case, if it is sunny or not, and if it is morning is 0, the probability of us going out to play is 0, because none of those examples exist. and if it is sunny or not is 0, and if it is morning, then the probability of us going out to play is 0.5. In same way, if the data is sunny or not is 1, then the probability of us going out to play when is football played is 1 is always 1, because in each of this instance you will see we do go out to play. And if it is 0, it is 2 upon 5, which is 0.4. I've made these calculations here. Feel free to pause and refer this. So our decision tree will look something like this. First, we take sunny or not. If it is 0, then we check whether it is morning or not. If it is morning, then we say, okay, there's a 50% chance that we'll be going out to play. If it is morning, if it is not morning, then we say there's no chance that we'll go out to play. If it is not sunny and if it is not morning, we will not go out to play. Makes sense. Then, if it is sunny, then we want to check whether football is being played. If football is being played, we always go out to play. If football is not being to played, then there's still a 40% chance that we'll be going out to play. This is what that if we were building only a two-step decision tree, this is what we will be building our decision tree. So the first we calculate the first split, where to make the split using information gain. We use information gain to calculate the second splits, and then we calculate the terminal probabilities in the terminal leaf. Uh, so if you want to write this decision tree of depth2 like a normal Python function, so it will be like if it is sunny or not, then we check if football is being played. If football is being played, we say 1, else we say zero point 0.4 because it's either being played or not being played. If sunny or not is 0, then we check whether it is morning or not. If it is morning, there's a 50% chance that we play. If not, then we don't play. I have added another thing to handle when some data is done, but feel free to ignore it. And then uh, we calculate the probabilities on our data. So you see, we have calculated the probabilities for each of the rows in our training data. The entire data is 0.4, 0, 1, 0.4, 1, 0.4. Now, how do we know that this is correct? Well, we can easily verify it using the scikit-learn library. So we just call sklearn decision tree classifier plot tree. Uh, we prepare our training data. Do note that we are removing the target and probabilities and data target. We fit, we plot our tree. As you can see, the tree is exactly the same as one we drew while using just theory. So you will see the tree is sunny or not, is morning, and then two terminal nodes, a football play two. Do note that I've also grown it to depth 2. If I grow it to depth 3, you will see different results. So let's just say if I go for depth 3, you will see that they get to this is different values. But since we have only gone to depth 2, and with such small number of samples, a 2 depth tree with 4 variables is more than enough. And then we predict the probabilities of the class 1 using this decision tree. As you can see, the probability is here, and let's just check out what were the probabilities that we calculated manually. As you can see, the probabilities are exactly the same using the decision tree which scikit-learn has built us and the decision tree which we manually built. Now, obviously, you can codify this logic into a class using the tree data structure and build your own decision tree. But mostly, you don't need to do it because scikit-learn has done it for you, done it already for you. So you don't need to reinvent the wheel. The most important thing was to understand how decision trees actually grown using Gini impurity and information gain. You can substitute Gini impurity with entropy. Feel free to read about it. If you want, I can post a video on it, which explains how information gain is calculated using entropy and decision tree is built in a similar manner. All right, I think that's all for the video. If you like the explanation, do like and subscribe to the channel. And for more further explanations, I do blog a lot, so do follow mlexplain.blog. Thank you for watching and have a good day.